In this video, we look at finding equations for a line in space. This is the first in a series of videos about lines, planes, and distance in three-dimensional space. In this video in particular, we're going to look at the parametric and vector equations of a line. We'll look at an example of how to find the equation of a line given a point on the line and its direction vector, and how to find the equations of a line given 2 points. Intuitively, this is just an extension of what we know about lines from algebra. So if I want the equation of a line in algebra class, well, two things define that line. I need some point on the line and the slope of the line. The slope is probably the most important part. When somebody tells you the slope is 2 over 1, you know that if whatever point it passes through, you're going to go up 2 and over 1, and you're going to find a second point on the line. So if our line contained the origin, I would go up 2 and over 1 and find another point, or up 2 and over 1 and find another point. So that's giving us some sense of the direction that that line is going in two-dimensional space. But I could have a line with exactly the same slope that passes through a completely different set of points. If our line happened to pass through the point x equals -1, y equals 1, and it had a slope of 2, we'd go up 2 and over 1, up 2 and over 1, and graph that line. And those are going to be parallel. So that slope is giving us a sense of direction, and the point on the line, or any one of the points on the line, is distinguishing it from all of the other lines that have exactly the same slope. In Calc 3, when we're looking at lines in space, or even lines in Rn, we need exactly the same thing. We need something to describe the direction of the line, to tell us which way that line is going in three-dimensional space, and then we also need a point on the line to distinguish that line from all the other lines that are going in exactly the same direction. I bet you can guess, well, we still need a point on the line to find the equation of a line. So we're assuming we're in R3, so I need a point. Can you guess what we would use for direction? If you said vector, you're absolutely right. So we need a point and what's called a direction vector. I'm going to call it V, and its components are A, B, and C. We'll call A, B, and C the direction numbers of the line. You might say, okay, Ms. Townsend, well, what does that tell me? Well, I know that x naught, y naught, z naught is on the line. And the direction vector, v, I'm going to draw that in red, tells you which way to go to find all of the other points on the line. So maybe this is v, and this is our line right here. We're talking about all of these points. So the vector indicates the direction, and that point distinguishes it from all the other points, or all the other lines, like this one over here, that have the same direction vector but pass through a different set of points. That has the same direction vector v. So I need this point, and that v is indicating the slope. So to come up with the parametric equations of the line, or even the vector equation of the line, I'm going to state the line state what we know about the line in a different way. So this line is going to be the set of all points x, y, z such that let's say the vector from x naught, y naught, z naught to x, y, z is parallel to the direction vector v. Say, okay, what does that mean, Miss Townsend? Well, it's just what it says. I'm looking for all the set of, or all points x, y, z, so such that the vector from x naught, y naught, z naught to x, y, z, this vector from here to here, is parallel to this one. That's all. If x naught, y naught, z naught were somewhere else so that it wasn't parallel, it wouldn't be on the line. So this always has to be parallel to this. Even if x, y, z is behind us, that vector is also parallel to v. So in order to come up with our equation, let's just write that down. This vector has to be parallel to the vector v. And we've got a couple of tests for parallel vectors. One involves the cross product. That's probably not the most convenient here. Well, what else do we know about parallel vectors? Remember, parallel vectors are constant multiples of each other. So I'm going to call this point P, and I'm going to call this the point Q. So the point from P to Q has to be parallel to V. And if PQ is parallel to V, that means PQ in component form has to equal a constant times V. And V has components A, B, and C. Now, PQ in component form, we're just going to take the coordinates of Q, coordinates of the terminal point, and subtract the coordinates of the initial point. So we'll have x minus x naught, y minus y naught, and z minus z naught. And that has to be equal to a constant times this vector ABC. Now, normally we use C for a constant, but we're going to use the variable t because we're going to think of it in a different way later. And if we're talking about the line that goes on forever in both directions, t can be any real number. So this has to be equal to this. Now a, b, and c are known. T is our independent variable. It's playing the role that x played up here. Remember, we had y equals mx plus b. If I vary x, y depends on x, so you can tell me what y has to be. Here we're going to vary t, and as I change t, I'm going to get a different x, y, and z. So I've got this vector equation. If I distribute the t over here, that's scalar multiplication, you just multiply all the components by t. Oops. This vector is equal to this vector if and only if the components are equal. So this has to be equal to this. The only way two vectors are equal is if their component forms are equal. So x minus x naught has to be equal to t minus, or to t times a. I'm going to write it in the reverse order, at. So I'm going to solve for x. So I have x equals x naught plus at. And similarly, the y component here has to be equal to the y component there. So y has to equal, if I add the y naught to both sides, y naught plus bt. And the z component on this side has to equal the z component on that side. So if I add z naught to both sides, I get z naught plus ct. All right, so these are called the parametric equations of the line. Now, if you give me an x naught, y naught, and z naught, that's our initial point, and you give me a direction vector with components a, b, and c, I can just substitute those in right here, and I'll have the equation, or the parametric equations of the line. So here's a very simple example. Let's say you're asked for the parametric equations. Of a line that passes through let's say -2, 1, 3. So I want to find the parametric equations of the line passing through this point and having, I guess, the direction vector. Let's say 4 to -5. Okay, writing down the parametric equations is very easy. After we write this down, we're going to talk about it a little bit, and we're going to look at our graphs to make sure that we truly understand what's going on. Okay, so according to our formulas, x is a function of t, y is a function of t, and z is a function of t. So I'm going to write that like this just to make it a little bit more explicit. That x depends on t, and it's given by x naught plus at. Now this is x naught, y naught, z naught. So my initial x value is -2. Actually, let's write these all down. They all start with their initial x, y, and z value. So I'm going to write down my x naught, y naught, and z naught right here. All right, so x starts at -2, y starts at 1, and z starts at 3. And then according to our formula, we just add the x component of our direction vector. That's a, b, c. A times t for the x. So I'm going to have 4 times t for the x. And then for the y, I'm going to add 2 times t. And then for the z, I'm going to add -5 times t. So there's some line in space that passes through this point and has direction vector 4, 2, -5. And it is completely described by these parametric equations. Now the parametric equations are not unique. We don't have to start with that point. We could have just as easily started with a different point on the line. So these numbers could be 3 different numbers, and it could still give us the same line. So keep that in mind. The equation of a line is not unique here, whereas it was unique before. If we wrote it in the order mx plus b, it was always going to be just maybe that written in a slightly different order. Like these, the x naught, y naught, and z naught could be completely different, and it could still be the same line. Okay, before we talk about this picture, I want to give you what's called the vector equation of a line. And this is a little bit of a preview of what we're going to do in the next section. We're going to talk about something called vector valued functions later. Okay. The input to this vector valued function is some real number. So I'm going to start with the domain. It's going to be a subset of the reals. And then we're going to map it to a point in 2-dimensional space or 3-dimensional space or n-dimensional space. But in this example, we're looking at lines in 3-dimensional space. So I'm going to take a real number t and I'm going to map it to a point in 3-dimensional space. For every t, you write this over here in this other notation. I'm going to take every t and I'm going to assign it to a specific point, x of t, y of t, z of t. So r of t has components. It's like a vector with components, x of t, y of t, and z of t. And we're actually not concerned about the whole vector. We're just looking at the end point here. We call this a position vector in the next chapter. We often call this the position vector because it's telling us what position we're at maybe a certain time, if that's what t represents. So if this represents time, this is the position I'm at that time. So the vector equation of the line comes from writing this way, and then you just replace x of t, y of t, and z of t with these parametric equations that you came up with right here. So we have negative 2 plus 4t, that's our x component, 1 plus 2t, that's our y component, and 3 minus 5t is our z component. So here's your x, and there's your y, and there's your z. Okay. So this is the vector equation of the line, and these are the parametric equations of the line. Now the vector equation of a line just takes the parametric equations and uses them as components. Now, we can think of this from a different perspective. Up here, we thought of t as just a multiplier. We said this vector has to be parallel to this vector. So this vector has to be a constant times the other vector. Now, when I go over to the next chapter and we talk about vector-valued functions, I'm not thinking of t as just some multiplier. Now I'm thinking of t as a time. So when time t equals 0, here, r of t is given by, or r of 0 is given by negative 2, 1, 3. That's that initial point. So at time t equals 0, if there's a particle traveling along this line in space, it's right there at t equals 0. And then you say, okay, well, where is it 1 second later? Well, it's going to be 1 second later, it's going to be at the end of v. So this was x naught, y naught, z naught. Over here at the end of v, we're going to start at x naught, y naught, z naught, start at 1 or negative 2, 1, 3. And then we're going to go 4 units in the x direction and 2 units in the y direction and negative 5 units in the z direction. So we get 2, 3, negative 2. In general, this is x naught plus a, y naught plus b, and z naught plus c. And say, well, that's t equals 0. Let's say 1 second later, t equals 1, we're here. And at t equals 2, we're going to be over here. We're going to go 4 units in the x direction again, negative 2, or 2 units in the y direction, and negative 5 units in the z direction. So if I start at 2, 3, negative 2, and I go 4 units in the x direction, I'm going from 2 to 6. And then I go 2 units in the y direction, so I'm going to go from 3 to 5. And then I start at negative 2 and I go negative 5 units in the z direction, so I'm going to be at negative 7. And so this is x naught plus 2a, y naught plus 2b, z naught plus 2c, And of course, we don't have to go in integer steps. What if where were we 1/2 a second later? Well, we wouldn't go all the way across v. We wouldn't cover the full length of v. We would just cover half of v. So in that case, t would be 1/2. And instead of going 4 units in the x direction, we'd go 2 units in the x direction. Instead of going 2 units in the y direction, we'd go 1 unit. Instead of going -5 units in the z direction, we'd go half of that, -5/2 or -2.5 units in the z direction. We can now think of this time, we can think of this variable t as representing time, and when t equals 0, we're at that initial point, and 1 second later we're over here, and 2 seconds later we're over here, and 3 seconds later we're over here. Or if we wanted to go backwards, 1 second ago we were at -v, and 2 seconds ago we were at -2v, and 3 seconds ago we're at -3v, and so on, and it goes all the way back in both directions. Now, that t equals 0 is arbitrary. We could have started counting at any time, and that doesn't necessarily have to represent time, but it's a convenient way to think about it. It's nice to think about x, y, and z being some position that depends on time, and this being what's called the position vector. We're not actually concerned about the vector part. The vector starts at the origin and it points right there. It says, there you are, and then at t equals 1, there you are, and at t equals 2, there you are. It's pointing at the current position. Okay, so we've talked about the parametric equations of the line and then the vector equation of a line. And we know how to find the equation, the parametric and vector equation, given a point and the direction vector. But what if you have 2 points on the line? What if instead of giving you the direction vector, I say, here's a line, and on this line we've got the point P, which has coordinates -2, 1, and 0, and then it also has the point Q, which has coordinates 1, 3, and 5. So I might ask you, I might give you 2 points. I might ask you to find the parametric and vector equations of the line. Now, given that this doesn't necessarily represent a position, either one of these could be x naught, y naught, and z naught. It doesn't really matter. There are lots of correct ways to write the equation of this line. So I'm going to think of P as my starting point, x naught, y naught, z naught, but I could have just as easily chosen Q to be that starting point. Okay, any ideas on how we find the direction of the line? It's actually very reminiscent of when you were in algebra class. Remember we said, if you give me 2 points, I can find the equation of the line, because what can I do with the 2 points? I can use the 2 points to find the slope, and once I have the slope and a point, I can use that to write the line. This is the same thing. I've got a point, I've actually got 2 points, but if I have 2 points, those 2 points together can give me the sense of the direction of the line. I don't know what v is, but v could certainly be the vector that starts at P and ends at Q. That would be fine. That's a fine choice for v. So let's do that. So if I give you P and Q, you can use those to come up with the direction vector. Either one of these, P or Q, could be your x naught, y naught, z naught, and then you just substitute everything in to those 2 forms that we talked about earlier. Okay, so let's find the direction vector of the line. I'm going to use the vector from P to Q. We start at Q. We take the coordinates of the terminal point. It has coordinates 1, 3, and 5. And then we're going to subtract the coordinates of P. So we're subtracting -2, 1, and 0. So that gives us a 3, a 2, and a 5. Okay, that's our V. Or if we prefer, we can put those labels on it, A, B, and C. Wherever you start, go 3 units in the X direction, 2 units in the Y direction, and 5 units in the Z direction to find another point on the line. And you can keep doing that over and over again. You can multiply that by a constant and do that, but you have to start somewhere, and then you can keep using this to get other points on the line. Just like you did in college algebra. If we had a slope of 2, we could just go from one point and go up 2 and over 1, up 2 and over 1, and up 2 and over 1. We're doing the same thing here, but we've got 3 directions. Go 3 units in the X direction, 2 units in the Y direction, 5 units in the Z direction. And then do it again. 3 units in the X direction, 2 units in the Y direction, 5 units in the Z direction. Over and over and over again. And that's going to give you all of those points that are evenly spaced on the line. And if you want all the points, you gotta multiply this by fractions as well. And irrational numbers, all of the real numbers. You multiply this by all the real numbers, and you add it to one of these points or the coordinates of these points, and then you get the whole line. Okay, so that's your ABC, and I've decided to use P as my X naught, Y naught, Z naught. So that's -2, 1, 0. So my parametric equations start with X naught, Y naught, Z naught. So I start with -2, 1, and 0. And then I'm going to add, since my X component of my direction vector is 3, I'm going to add 3 times T here. Because wherever I start, which is the -2, I'm going to go 3 units in the X direction to get to the point I would be at 1 unit later. When T equals 2, I go 6 units in the X direction from -2. When T equals 3, I go 9 units in the X direction from -2 to get my new X coordinate. So we just keep going 3 units in the X direction for all the multiples of T, but then also any value of T would be fine. T could be 1/2, we could be interested in a half a second later, or 1/10 of a second later, or square root of 2 seconds later. So T can be any real number. But we're going to take this X value that we started at, we're taking this X location, and we're going to take that component of V, that 3, and we're going to multiply it by T to get all of the other X values. With Y, we start at Y equals 1, and we repeatedly go 2 units in the Y direction, forwards and backwards, to get all of those integer multiples, and then of course we could make those fractions and irrational numbers as well. And then we go 5 units in the Z direction. So this is tracing out our entire curve. Normally we don't write the +0 here, but these are the parametric equations of the line. And if I want the vector equation, R of t has components x of t, y of t, and z of t. So I put my x of t right here, y of t right here, and z of t right here. And this is the vector equation of the line. So it's very similar to what you did in college algebra. If I give you 2 points, you can find the slope in college algebra or pre-calculus or high school algebra. In this class, if I give you 2 points, you can find the direction vector. It just tells you which way to go to get all the other points on the line when you start at one of the points. And so that's it for lines. I'll make another video for planes very shortly.